talk is going to be on measurement of Higgs at FCC with E plus E minus or the hadron. So Michael is a research staff at CERN. He's a member of CMS collaboration since 2008 and member of the FCC collaboration since 2016. He has been coordinating various physics studies for the FCC-hh and took part in a detector design in preparation for the FCC conceptual design report for the European strategy updated for the particle physics in 2019. He is currently coordinating FCC Higgs physics group as part of the feasibility study. So with this, may I request Michael to start his presentation on Higgs at FCC.
Okay, thank you for the introduction. So can you see the slides?
Yes, pretty clear.
Okay, great. So I'm going to talk about Higgs measurements at the FCC, and I thank Jenny for kindly introducing the hot topics for this talk. And I will start by presenting the present state of affairs, which we all know about, which is the Higgs discovery in 2012, which was discovered in the Higgs to gamma and Higgs to ZZ channel. And from discovery, we are slowly moving into the precision realm for Higgs physics. As you can see here, we're starting to pin down Higgs properties, the Higgs mass, and the various Higgs couplings. And this will be even more true in the future. So one of the main goals of the HLLHC is to further measure the Higgs properties. As you can see here on the left, there is the projected measurements for the HLLHC on the various Higgs coupling in the kappa framework, and on the right, one of the flagship measurements of the HLLHC, which is the measurement of the Higgs potential through di-Higgs production. Now, as you can see, all of this is great, but at hadron colliders, of course, one misses a few things, especially at the LHC. One misses model independence. And then there are couplings which can be measured, but not with exquisite precision, such as the light couplings, the ones that couple the least to the Higgs, because they have small mass, the Higgs to charm, Higgs to muons, the invisible decays, the total width, which also is connected to the fact that we would like to have model independent measurements. So at the hadron colliders, one has to make assumptions on invisible Higgs decays. Of course, the Higgs self-couplings, which one can potentially have evidence for di-Higgs production at HLLHC, but not for a precise measurement. And of course, beyond the standard model Higgs. So a very quick introduction on what's different in EE and PP collision. This was already briefly mentioned by Jenny in the previous talk. Now, of course, a proton is a compound object, which means that the initial state is not known event by event because we are colliding partons, and this already limits the achievable precision because you have to fold in the inputs from parton distribution functions. Another big limitation of hadron colliders is, of course, the extremely high rates and the QCD backgrounds, which also leads to having complex triggering schemes with high levels of radiations. Of course, the cross sections are large, both for your signal and your background, but if you're interested in electroweak type process, which is like, for example, the Higgs, you're going to have to fight with extremely large backgrounds. On top of that, your initial and final states are color connected, which adds complexity to your reconstructed events. But of course, the advantage of PP collision is that you can go to extremely high energy because in a circular mode, you are not limited, or at least you're less limited by synchrotron radiation, and then your hardest limitation is the field or the actual size of the collider. On the other hand, on on E plus E minus collision, your initial state is extremely well defined. You can do polarization, especially in linear colliders, and you can, of course, aim for high precision measurements. You can almost be in triggerless readout modes. You have low radiation levels, and you have, of course, higher sensitivity to electroweak states because you are colliding leptons. And then Of course, circular colliders and linear colliders have different advantages, which I will go through later. But mainly, linear collider can reach higher energy and can do polarized beams, whereas circular colliders can lead to very large luminosities. I have inverted the screenshots of the event displays here. My point here was to just quickly show how a Higgs event looks different in a E plus E minus environment, which is actually here on the right, which is a X plus Z production mode, the external mode, where the X go to glue and the Z to dimuon events. And you see, even if you are a jet events, you have extremely low multiplicity in your event display. And this is a X to Z in a leptonic final state, which should be one of the cleanest decay modes of the Higgs, and you see how much other stuff you see in your detector. So a bit more in detail, what are the future proposed machines? This was already discussed, so I can go quickly here. FCC-ee, CPC, these are very similar machines. Of course, here you are limited by synchrotron radiation in how much center of mass energy you can reach, because the electrons have very low mass and they can lose a lot of their energy from emitting photons. But of course, the advantage here is that you have extremely high luminosity at low energy at the Z, more than a W than the Higgs and then the top. And of course, the advantage of having circular collider is also that you can collide in different points. So potentially you can have even 4 interaction points here. ILC and CLIC are the 2 proposed linear collider machines. These can reach, of course, very high energy, which have several advantages, which were talked about in the previous talk. In addition to polarization, you can also directly reach the threshold for producing TeH, Day5, and of course, you can also do very well Higgs physics with such machines. In terms of PP, as I said before, this can give you the reach to having extremely high center of mass energy. And this is because the mass of the proton is much higher than the mass of the electrons, which means you are not limited from synchrotron radiation. What limits the actual total momentum in a circular machine is either how much how strong is the field of your dipoles, or how large is your ring. So given how much if you know you can do 16 Tesla magnets, then you can ask what is the best collider that you can do. Of course, you have extremely high luminosity, which also means you have high rates, large cross section for strongly produced processes, large QST backgrounds, because alpha strong is 10 times larger than alpha electromagnetic. This already said, you have colliding partons, which means that not all of the center of mass energy is available. You have pileup when you go to high luminosity. And of course, these are typically thought as discovery machines for heavy new states. But also thanks to very high rates, these are also well suited for precision, as I will discuss later. There are several possibilities for a high energy hadron machine. One is a high energy LHC, where you take the LHC and you put 16 Tesla magnets on. This will allow you to simply double the center of mass energy. This is another option which was explored at the time of the European strategy update, which is a low energy version of FCC. So you build a 100-kilometer tunnel, but you put in the cheapest possible magnets that you can find, which would allow you to get to 6 Tesla. And this would lead to a center of mass energy to about 37 TeV. And then, of course, the dream machine, which is a 100 TeV machine, where you put 16 Tesla dipoles in, and this gives you 100 TeV center of mass energy. So within the European strategy update of 2019, the CERN has formed these collaborations called FCC, which had the goal of studying all of these possible machines, which I already discussed, PP collider, FCC-hh, and E plus E minus collider as a potential first step, and then also to study the other options, which I will discuss less. But you can find most of the details in the documents which I have linked in the previous slide. This is a potential timeline for the integrated project. Now we are here. in the so-called feasibility study, which will take 5 years. This is mostly for engineering purposes, understand if there are geological investigation and understand if one can actually dig the tunnel in the Geneva area and see if the local authorities are complying, and how feasible is this in practice, and having concrete plans. But of course also in trying to define something like protocol collaborations to understand possible detector designs and optimize the detector design and the requirements for maximizing the physics potential. Now, during all this time, there is going to be a R&D, extensive R&D done on superconducting magnets, because today we are not able to do a collider-proof 16 Tesla magnets, and this is probably going to take from 10 to 20 years. And there is extensive R&D going on, and this would lead to a potential, FCC-ee start by the end of the HLLHC. Of course, there is some time needed for installation and so on, which is around 2040. This would lead to 15-ish years of operation for FCC-ee, and then of course FCC-hh could start late in 2070 to 2090. So this is a very long time scale. It can be scary, of course, but it also means that you dig a 100-kilometer tunnel, but then you have a physics program that can last for the full century. Now, more in details for the FCC-ee. This is the first machine for the integrated production. This uses this top-up injection scheme, which was developed also for Bell. The baseline design has 2 interaction points. However, of course, nothing limits to have 4 interaction points. This comes at the sacrifice of the instantaneous luminosity per interaction point, but since you are multiplying by 2 the interaction points, you actually gain in total luminosity by a factor around 1.7. This is a plot which was, I believe, already shown in the previous talk, which shows the difference between linear collider machines, which typically have this profile of luminosity which grows with energy, as opposed to circular collider machines, which have this luminosity profile which goes down with energy. This is the FCC-ee run plan. So the idea is to have around 4 years at the Z to measure extremely well the electroweak sector, then to have the WW mass scan around 2 years. Again, this would allow to measure the W mass, for example, to half MeV. And then what is interesting in this talk here is the X2, the extra long mode at 240 GeV. You can notice that this is 240 as opposed to 250 for the linear colliding machine, and this is due to the profile of luminosity which falls. So here one maximizes events by going at 240, and this one could run at this mode for 3 years. Would lead to around 5 inverse Satoburn if one has 2 IPs, and around 8 to 10 inverse Satoburn if one has 4 interaction points. Then of course the TT bar thresholds, which one could run 1 and 4 years respectively. Of course, these are different operations which are made for the measurement of the TT bar cross section, but also, as I will show later, these highly benefit Higgs measurements. And this is also a tentative plan for the FCC run plan, the Z pole, and the WW, then the Higgs Z, and then the top, of course, with integrated luminosity, which goes down because of the synchrotron radiation. So just to give you some numbers for the Higgs. So this is the cross section for the various Higgs processes as a function of center of mass energy. This is a zoomed version of the plots you have seen in the previous presentation. Again, as I see, the maximum of the cross section for extra long is at 250, but the FCC-ee chooses to operate at 240 because you have a luminosity profile which falls very steeply, and it actually you actually collect at the end more events at 240 than 250 at the end of the day. Plus, you have a slightly less boost of the final state, which improves some of their reconstruction. Then you have the 340 to 360 GeV points, where your Higgs where your WW fusion cross section starts to get sizable, around 30% of the total. and will actually also lead to improved precision in the Higgs measurements, not only directly due to the improved statistics, but also because it provides complementary measurements. In particular, it's needed for the total Higgs width. Just to give you an idea, these are the numbers one expects at the different Higgs, at the different working points of the CC machine. Of course, the number of Z is spectacular. At the end, you are going to produce 10 to the 15, but for the Higgs, when you run at 240 GeV, you're expecting around 1,000 Higgs per day. So at future E plus C minus machine, the physics background are pretty small. You have two types of background, of course. You have the background position S channel, which typically cross-section is falling like 1/, center of mass energy. So, and then you have the T channel like background, which typically grow like a logarithm of the energy. Again, this is a pretty obvious statement, but one has to deal with the typically larger signal over background, the T plus C minus collider, because both your signal and your background are of electroweak type, so they have roughly the same order. Whereas if you are interested in an electroweak type of production at the hadron collider, you have to fight with much larger background. So at the FCC-ee, as in any E plus C minus collider where the initial state is fully known, the flagship measurement for doing Higgs physics, and this was already introduced in the previous talk, is the so-called Higgs mass from recoil, where you simply reconstruct the decays of the Z, for example, into dimuon, which is extremely clean, and this allows you, just by energy conservation, to reconstruct the full form momentum of the Higgs without having to explicitly reconstruct the Higgs decay. This is done by using this formula. It's pretty trivial, and this is the kind of plot you can expect when you reconstruct the recoil mass. So you have like very clean Higgs peaks on top of a Z star and WW star background. Now, what this allows you to do is that you're basically measuring the total cross-section of Higgs Stralsund, and this is typically of the order of the amount of Higgs which are produced, which you expect around 10 to the 6 million. So, you know, if the rate is growing like coupling square, which is basically the only unknown quantity in this process, you expect typical precision of the Higgs to ZZ coupling of order per mil, simply because you have directly access to this coupling by doing this measurement. And then, of course, what you can do is you can measure ZH, then Higgs going to ZZ, which also is proportional to the Z coupling, but also to the width, because you have to fold in the branching ratio of the Higgs. And if you measure this and you measure the total cross-section as before, then you can actually have a measurement of a direct measurement of the Higgs width of the order 1%. And then you have all the other. So once you have the total width, then you can directly normalize all of your Higgs explicit decays, which you measure X2BB, X2CC, X2 muons, and you can directly translate this in a coupling measurement because you know the width at that point. So another thing you can do is that if you go to 360 GeV, as I was saying before, the total cross-section for WW fusion is only 30%, but this allows to make complementary measurements as opposed to the 240 GeV. You can see that you can actually measure the nu H to nu BB, which is proportional. So if you have the X decaying to BB, this process is proportional to X to WW coupling and X to BB coupling divided by the X width, because the X, again, you're folding in the branching ratio. But then at the ZH threshold, we have already measured ZH to BB and ZH to WW. So if you make a ratio of these two things, this amounts simply to a coupling, X to ZZ coupling to the fourth divided by the X width, which also gives a precision of order 1%. And then what you can do is you can actually measure the nu H, where the X decays to WW, where you have the WW both in production and decay, which gives, again, a total rate which is proportional to the X WW to the fourth coupling divided by the Higgs width. And since in the previous mode you have already measured WW, then this allows to give you a GW2. Sorry, in this mode here, you have already measured this GZ X to ZZ coupling to the 4 divided by the X width. And if you make the ratio of these two things, you actually can measure the ratio of the W coupling and the Z coupling, which you already know this by per mil level. So this gives you a WW precision of order per mil. Of course, this channel is going to be a bit more limited. So all this story to say that running at the top does not simply add statistics, but it gives access to different combination of couplings, which allow you to better constrain these things. Now, this is just to give an intuition, but at the end of the day, one will do a full kappa fit framework, or even better, a fit in the SMEFT framework. So this is just a table to summarize what each of these measurements in terms of really branching ratio precision give you as expected at 240 and 360 GeV. And you can see for the abundant decay modes, such as X to BB, X to glu, and even X to CC, or X to tau tau, you get percent level precision just in terms of statistical precision. Whereas you have some modes, for example, X to gamma gamma, X to mu mu, where you are still statistically limited because you only can produce so many Higgses at the plus and minus machine, order 1 million, and these branching ratios are order 10 to the minus 4. So you will not be able to achieve exquisite precision on these decay modes. So just a couple of flashes on what one can do in at the plus and minus machine. So for example, the X2 quark couplings, BB, CC, glu, and strange. So these are the numbers from the European strategy update. You see that the expected precision for kappa C, kappa S, and kappa D, these are the most rare decay modes. So except for kappa C, one does not reach the precision for kappa S and kappa D, because of course the strange Yukawa is very light, and therefore the X2 strange branching ratio is very small. But with the recent development in charm and strange tagging, this number can actually improve a lot. One has to build detectors for FCC-ee, which can maximally exploit the physics one wants to do. In terms of Higgs physics, there are several possible requirements, which I'm going to sketch here. So the Higgs mass and WW and the Higgs cross-section is basically limited by how well you're going to reconstruct the tracks, so your muons, because these are going to limit the resolution. In the tracker, the X to BB, CC, and glu is how well you're able to construct heavy flavor taggers that can disentangle these hadronic modes. And of course, one way to do this is to have extremely good vertexing detector that can disentangle these modes. The X2QQ to VV, so where the VV is WW and CC, of course, you want to be able to disentangle these modes. And this will be done by having a very good jet energy resolution. And of course, X to gamma gamma, which is one of the rare decay modes. Of course, one wants to have a good resolution. So as a baseline in the FCC-ee, there are two considered detector. One is the CLD, which is basically a scaled down version of the click detector. This is a very consolidated option because it's based on a detector design which exists. This is also allows to do full simulation straight away because this detector is fully implemented in the FCC software. The tracker is purely silicon based. There is this 3D imaging calorimeter, which was already mentioned before, which is this silicon tungsten sampling calorimeter, which allows to do a particle flow with good precision. Then you put the coil also outside the calorimeter system to avoid having too much interaction lengths and radiation lengths before the calorimeter and not degrade your particle flow reconstruction. So this is a proven concept and understood performance. And there is a more ambitious proposal for low energy FCC, which is the idea detector, which use this extremely light tracker based on drift chambers. So this is gas, is actually lighter than air. So it allows to give extremely low material. So, and this gives extremely good track reconstruction. because it minimizes multiple scattering with having a silicon vertex detector using these maps, which are used for the ALICE upgrade. This dual readout calorimeter, which allows to do event-by-event compensation between the electromagnetic and hadronic showers, which also gives extremely good hadronic resolution, and also having a thin and light solenoid. Then we are also working on a third detector concept based on liquid argon calorimetry, which has been proposed as well. Highly granular liquid argon. This is inspired by the FCC-hh. Just a few flashes of what you can do with this ambitious detector. This is the idea detector. You can see the total radiation interaction length in the tracker at 90 degrees is around 5% of X0, so it's extremely light. This allows to do extremely precise charge tagging. So here you can see the performance of charge tagging. And we also explore the possibility of having a fourth vertex layer closer to the beam pipe to see what is the possible improvement in performance. This is of course crucial because it allows to isolate the BCC and glue decay modes. Something also we have been exploring recently is the use of particle identification, which is not only useful for flavor physics, but it's also useful for doing Higgs physics. In particular, if you want to do Higgs to strange, your strange jets will be heavy in will be highly populated by kaon content as opposed to pion content, and you want to be able to identify this. And of course, at low energy, at low momentum, the best way to do pion to kaon separation is time of flight. At high momentum is the NDX or DDX, and this is something these drift chambers are highly well designed for. And this is the performance of a strange tagger for different assumptions, whether one uses a PID or not, or for different assumptions of the timing detectors. And you can see that actually you can get to pretty ideal performance, which is this peak curve here, if you have already a 30 picosecond level timing precision and the NDX as shown there. So X2 gluon, this is of course very interesting per se because you want to measure the X2 glue coupling, the effective coupling, and you can do gluon tagging if you use all the particle content information in the event. But it's also interesting for people who do QCD and want to understand the gluon fragmentation in an extremely clean environment without having to deal with the quark contamination, especially also contamination of color connection between initial and final state. So this will allow you to isolate this extremely clean 100,000 X2 glue sample in a plus minus machine.
Michele?
Yes.
The previous slide?
Yes.
The top left plot, what exactly it is?
Well, this is a jet. Well, it's a shape observable built by a theorist that pinpointed the fact that one model versus another show extremely different performance, and in fact, if you could measure these things, would allow to better constrain it.
Mm-hmm.
So this is Peter and Herwig. So the Higgs recoil method is going to be used for the Higgs mass and cross-section measurements. So why one wants to measure the Higgs mass? One needs a 10 MeV precision for a per MeV precision of X2ZZ and X2WW couplings, simply because these are inputs for this for the branching ratios. Order 4 MeV would be able to constrain further the electron Yukawa. But nevertheless, this is a very important measurement because we have discovered the Higgs, we want to measure it to the best possible precision. Just purely from statistics, you expect a 6 MeV. This defines also very stringent detector constraints because you have to measure this in the mu channels. And again, as I said before, the less material you have in your tracker, the better the resolution. And here we already did some studies showing what is the impact, for example, having a full silicon tracker versus having a gaseous tracker. You see the impact is sizable, or having a higher magnetic field as opposed to having a 2000 magnetic field also improves a little bit the resolution. X2 invisible, of course, the X could be a portal to dark matter or to other new physics. And in the standard model, X decays to invisible via ZZ to neutrinos. The branching ratio is extremely small, 10⁻�3, so it's very hard, plus it's missing energy. You can also do this recoil method to reconstruct the Higgs. So this was studied in the full decay modes in EE, mu, BB, and QQ for the Z. So one will reconstruct the recoil by making a separate analysis in all these decay modes. And the statistical uncertainty only, one can reach the standard model sensitivity at FCC-ee, which is pretty spectacular. And this also means that there is potential for discovery of X2 invisible for a branching ratio, which is around 5 times larger than this. Something else, of course, this is very speculative, but would be the electron Yukawa measurement, the direct measurement of electron Yukawa. You cannot really measure the electron Yukawa by doing X2-ee decay mode because the electron is too light and this branching ratio is extremely small, so you barely have one event, even if you decay 1 million. But you can use E plus E minus to H, a bit like a Alamuon collider, and you make use of the fact that you have extremely high luminosity in a plus E minus machine, in a circular plus E minus machine. Of course, this means that you need, as channel and beam monochromatization, you need to know the beam energy to extremely high precision and the Higgs mass to extremely high precision. Just the ISR plus FSR leads to a 40% in the beam spread smearing, plus the ISR leads to a broadening of the Higgs width of the perceived Higgs width to a 40%, plus you have beam spread, which leads to another 45%. So basically, it means that since the Higgs is extremely narrow, it has a 4 MeV width. You have to shoot exactly the right energy, but given that you cannot constrain the beam energy to such precision, you basically are losing basically 80% of this. The X2 glue channel seems to be the most promising because it's the most abundant, and one can hope to separate it from the overwhelming Z to jet background with the glue and tag I showed before. So if one were to run 4 years at the 125 GeV, one would be able to almost reach standard model sensitivity for the electron Yukawa, which compared to other colliders is extremely impressive achievement, as you can see in this plot here. Of course, one would have to decide whether this is feasible or not. The Higgs coupling, okay, I don't need to motivate why the Higgs coupling the Higgs self-coupling is important. We have barely measured it. We are going to barely measure it at the HLLHC, and the future machines are definitely going to be giving us more handles on them. At FCC-ee, of course, you don't have enough steam to produce directly to Higgs on shell. So the way you can constrain this is by measuring the ZH cross-section and the new H cross-section to extremely high precision and indirectly extract the precision of the Higgs self-coupling. If you have 2 energy points, again, at 250 and 365, this allows you to also resolve some degeneracy there is, because this process is actually sensitive to both the Higgs self-coupling and the WWHH coupling. So this was already discussed, I think, in the previous talk. And with 2 interaction points, with the 1% precision you expect on the cross-section, you can extract the self-coupling to a precision of 40%. This is done with a full EFT fit. If you do combine with HLLHC, this leads to 33%. And if you have actually a full 4 interaction points, this could actually lead to a 25% precision. So this is the total, the final sensitivity for most of the Higgs decay modes and the Higgs couplings actually at FCC-ee, only with 240 with 365 GeV, and you can see that among all the proposed A plus E minus machines, this seems to be the one which gives them the highest precision, with the exception of specific decay modes or couplings, such as TeTH, which you cannot reach, or di-Higgs. So for the abundant decay modes, of course, the FCC is the one which provides the best sensitivity for single Higgs coupling measurements. Now, this allows me to transition a little bit to FCC-hh measurements. So at the TeV collider, one can only measure production times branching ratio, and we don't know the total width, as I already mentioned, plus the production cross-section is subject to large uncertainties, both from PDFs and from theory uncertainties, because QCD is harder than electroweak. And in order to perform global fits, we have to make model-dependent assumptions. So instead of performing measurements of a ratio, instead one can perform measurements of ratios of branching ratio hadron colliders, such as X to XX divided by X to ZZ, which allow to cancel both production and width uncertainty and width, which means that you are actually able to make a measurement of a ratio of couplings. And since you actually know one once you have measured the Higgs to ZZ coupling at the plus and minus collider, and you know this at the Fermi level precision, this allows to give you an actual normalization for every coupling you would measure at the PP collider. So if you actually measure, if you go to a PP collider after an plus minus collider, you basically are able to convert the Higgs to any Higgs coupling to an absolute any Higgs branching ratio to an absolute measurement of the coupling. So this gives the extraordinary synergy between the two machines. Another synergy between an plus minus machine and 100 TeV machines is what I mentioned earlier, is that an plus minus machine is extremely good for measuring copious decay modes, the one which happen abundantly. But as soon as you reach the statistical limit, of course, you are limited, which is also another thing where the PP colliders can help on top of having model independent measurement. Thanks to the complementarity I discussed earlier. So for example, if you look at Higgs to mu mu, Higgs to gamma gamma, TeT Higgs, Z gamma, which is also very rare decay, and Higgs self-coupling, this is where you need to go beyond the FCC-ee or any lepton machine for that matter. The machine specification for FCC-hh machines. So this is just a quick glance, just to give you an idea of the challenge. So a PP machine at 100 TeV would have a typical luminosity, which is 6 times higher than the high lumi LHC, which is already very good, very high, which already produces around 200 pileup interaction per bunch crossing. So this would lead to around 1,000 pileup. This is, of course, extremely challenging for the detector design standpoint and in terms of performance that one has to achieve. This also produces a lot of radiation in your detector, which means that you will have to do lots of R&D to make your detectors radiation hard enough, especially the inner detectors, which are the most exposed. I don't have time to discuss these aspects here, but I'm happy to answer questions if you have. Of course, one of the key aspects is that you will need to have precision timing, which goes well beyond what we can do today. So we know from studies that around 3 picoseconds will be necessary. So just to give you an idea of how one can build some intuition how the cross-section scales for 100 TeV. So one can write the cross-section simply as the partonic cross-sections times the parton luminosity, which gives you a bonus at higher and higher energies. And in fact, you can actually compute the ratio of a cross-section 100 TeV to a 14 TeV by simply looking at the scale of the process and this exponent, which is given by where you are in terms of the parton luminosity as a function of the scale of the process. So basically, if you are at very low energy, your exponent is small, your gain is small. If you are at high energy, at high scale, your gain is large. This is obvious. If you want to produce a 10 TeV resonance at a 14 TeV collider, your cross-section is 0, whereas at 100 TeV collider, it will be extremely large. This is what you see in this plot here, the ratio of cross-section for extremely high mass processes as opposed to low mass processes. The Higgs sits in between. The Higgs sits, so if you want to produce a Higgs at threshold, you can see that already glue Higgs, which is one of the dominant production, is the dominant production mode actually at the LHC, will be still, of course, at the FCC-hh. You gain a factor 15 in cross-section. But the more you gain in the scale, so for example, for a Day5 process, you gain more, you gain 40. For TeTH, you gain 55. If you're interested in producing a Higgs which has a boost of 1 TeV, you gain a factor 400 in the cross-section, which is extremely large, right? And so these are things you can exploit at the 100 TeV machine. Another thing which one can notice that the levels of pileup will basically scale as the interstellar luminosity, and the PP collision, the PP cross-section, the total inelastic plus elastic cross-section doesn't increase much by 100 TeV to 14 TeV to 100 TeV, but your interesting process do. So it means that they will stick out more. So in some sense, you relatively pay less in terms of background, which is a bit counterintuitive. Now, in terms of kinematic coverage, of course, you have a different type of profile. Now you have more possible imbalance between the partons in the protons, which means that for the same energy, you're going to produce you're going to produce for the same energy scale of the process. For example, you look at the Higgs, the Higgs will be distributed among a larger pseudo rapidity. So this is what you can see here for Higgs to 4L or VBF Higgs. So this is the jet, the most forward jet in VBF Higgs will be peaking at eta 5, whereas at LHC it peaks at 3. And this is the eta profile of the leptons from the Higgs to 4L. You see that they extend to larger rapidity. So it means that you have to have a more ambitious goal for your calorimeters and your trackers in terms of rapidity coverage. But this is also extremely challenging because these are the rapidities where your radiation damage and your pollution from beams, etc., is the largest. So of course, this is if you want to record all of these particles, because you have also extremely large cross sections, so you might decide to not do that. In fact, if you actually look at the rates at large PT, you have more than 1 million Higgses produced with the 1 TeV transverse PT, transverse momentum. Actually, if you actually look at the probability for the various decay production modes, you have more probability to produce a Higgs from TTH at large PT than from a gluon fusion at some point. But this also gives the opportunity to study the Higgs in a very in a new dynamical regime where it's extremely boosted. And the XPT spectrum is actually very sensitive to new physics. This is shown in this plot here, where you look at the gluon fusion X production via the EFT or via the full theory. You can look at the PT spectrum is completely different, which means that whatever runs in this loop can affect the X production extensively. If you go to high boost, the Higgs will decay inside a very narrow cone, which also sets severe constraint on the granularity of the detector. At the LHC, we are not used to such large PTs, especially in terms of Ws and Z and Higgs. So you will be producing Ws and Higgses at 5 TeV. There will be many, but there will be. And so this means that these decay products will be extremely collimated, which also sets a constraint both on the momentum resolution of the high energy tracks and on the angular separation of your calorimeter, which calls, of course, for particle flow. This is one possible baseline of an FCC-hh detector, which could do the job, but this doesn't mean it's the optimal detector, but this covers the full rapidity range I was discussing. Think this as a big atlas detector with 2 LHCb plugged in at each side, with the difference that these are solenoids and not the dipoles as an LHCb. Okay, this I can skip. This is just to say that this larger dynamic range gives the opportunity to study the Higgs at large Q square, which also gives access to important high order operators. This is a reminder of the various cross-section increases at high energy. So again, TTH is 60 times larger, which gives a factor, a large factor improvement. If you want to have some intuition, if you fold in both the cross-section and the expected luminosity, you expect a factor 100 in terms of rate from the LHC, which gives around a factor 10 reduction in statistical uncertainty. From the experimental point of view, having so many Higgses at high boost also gives you access to a different phase space where your samples are actually cleaner, where pileup matters less, where you reconstruct objects with much higher purity, which means also that you can leverage the fact that you have lower impact of systematic uncertainties. We studied this in the case of TTH production, where you can actually measure TTH over TTZ to get rid of the theory production, because these are two very simple, very similar process, and the luminosity uncertainty in the X2BB mode, which makes these two decays extremely similar. Also, the experimental stochastic on the B is cancelled, and you perform a simultaneous fit on the Z and the Higgs peak, as you can see here. And this can give you a precision on the top Yukawa to the percent level precision. Of course, this also assumes that you know the TTZ coupling to percent level precision, and this also falls back to having an plus and minus machine, and particularly the FCC-ee machine before, which can give you this coupling to a percent level precision. The various Higgs decay modes, the rare ones I was discussing before, gamma gamma, Z2 leptons, Z gamma mu mu. The idea here is that, of course, in practice you will do it by fitting the full phase space, but if you actually restrict yourself to a high momentum for the Higgs, you can see that you can expect lower statistics, at least lower systematics, at least at this level. You can, I mean, at this level of in time, you can trust the systematics you put in for larger momentum photons, muons, and electrons. And you can actually study this in various decay modes, and you can see that you can attain percent level precision on all these decay modes. And if you measure the branching ratio of any of those decay modes to X to CZ, you can see that this is for various Higgs PT, you can see that you can actually get to again a percent level precision, and therefore you can exploit the fact that now you already know from the FCC-ee, the X to ZZ coupling to very high precision, around 2 per mil, which means that now you have a percent level precision on the X to mu coupling and the X to gamma coupling. The X to invisible, this also can be done at hadron collider. It is already done at the LHC. We measure Higgs plus X at high, momentum, where the Higgs decays invisibly. So you're basically fitting the missing ET spectrum in PP collisions. The largest background is going to be Z to nu plus jets, of course. In a low statistics regime, you're going to be constraining this by exploiting the fact that theories can actually predict Z plus jets over W plus jets and gamma with a very good precision, and you can actually extrapolate from control regions from W and gamma plus jets, whereas at high statistics you can actually measure the Z to nu spectrum from E plus E minus and nu, and then extrapolate back, and this also gives you a very good precision. Now you can actually see as a function of luminosity which kind of precision you would expect from the FCC-hh for X to invisible, and you see that after a few inversatobar, which in the lifetime of FCC-hh is not much, you actually reach the standard model X to ZZ floor, and you can actually go much beyond that. You can actually measure this branching ratio with some precision.
Michele?
Yes.
This one, which production mode is being used?
I think this is just a gluon fusion.
Okay.
But this indeed can use also TTH and NVH. Yes.
VBF is the best at LHC.
Yes.
But in this one, you are suggesting H plus X, or H goes to invisible, and okay, it's gluon fusion, so hadron.
Well, it's a MET plus jet analysis, right? But if you do VBF or TTH, you do exactly the same. Well, TTH gives you more handles, of course. But VBF, I mean, VBF, the problem is also you're losing a lot of sensitivity because you have to trigger on it, right? FCC-hh is going to be probably also more, yeah. So. Okay, these are additional ideas. Maybe I see that I'm maybe running a bit late. So additional ideas on how one can exploit ratios of measurements and correlated sets of systematics, for example, using the photons and electrons, which have a very similar systematic, and WH to WZ, for example, to actually extract, combinations of couplings and branching ratios. And you can see that with the extremely large statistics that you have at the FCC-hh, in the boosted regime, especially, where, again, to this date, you could probably trust more these measurements because your backgrounds are falling more steeply and your background contamination is smaller, then you can reach percent level precision in these combinations of coupling, which you can then reinterpret inside a properly done EFT and kappa framework fit. Now, of course, then the flagship measurement of the FCC-hh is the Higgs self-coupling measurement. This is a hard measurement at any collider, both linear, plus, minus, circular, etc. And the reason being that you are interfering two processes, one which is not depending on the self-coupling and one which is, where plus they negatively interfere, which means that you're basically losing as opposed to just adding these two. And then at ILLUMI-HC, you measure this at 50% precision. At the FCC-hh, as I said, you expect a factor of 40 increase in cross-section for this process and a factor 10 in luminosity, which means that you have around 400 times larger event yields, which, square root of this is around 20 in precision. So you expect around 2 to 3% precision on this measurement. Of course, this is if you were to be statistically limited. In real life, these are complex measurements which have B's in the final state and production uncertainty and luminosity uncertainty, which make this a bit more challenging. These are the decay modes we looked at. Now, the principle of these measurements, of course, is that you measure both the rate and the slope of the variation of the cross section as a function of k lambda to extract the self-coupling. And these are the final plots you get for the BB gamma gamma for B, BB, 4L, and BB tau tau. This does not include the full list of channels one could actually do, BBWW and the other decay modes of the Z, which will actually improve things further. These have been studied for different scenarios, and these are the final sensitivity in each of the decay modes. For BB gamma gamma, this is the combined. This is the actual precision as a function of the integrated luminosity, where you can actually read how much luminosity you need to get to the 2 to 3% level precision. At the end of the day, depending on which detector scenario and systematics uncertainty scenario you pick, in the most aggressive case, you measure this to a 3% precision. In the most conservative case, you measure this to a 8% precision. But this, of course, sets the type of challenge one will have to encounter when designing an FCC detector, because, of course, we will have to, build a detector which allows for this kind of precision, and also have theory uncertainties which are at the level that will allow for such a precision. We also studied the actual precision as a function of k lambda, because that there are scenarios which are preferred, which will lead to larger levels of k lambda. This is shown here again. I don't think I will go into details. This is the summary of the Higgs direct measurements at the FCC-hh in terms of production cross sections and ratio of branching ratio, which I mentioned earlier. I leave them here for completeness. But the bottom line is that you have percent level precision on the production times branching ratio on most rare decays, and percent level precision on couplings if you have an absolute measurement of the Higgs to ZZ coupling at the FCC-ee. This is the combined table with the FCC-ee, which shows that you basically pin down most of the couplings to percent level precision, with the exception of the Higgs self-coupling. These are possible other measurements that you can do at the FCC-hh, which are also relevant for the Higgs and which will set constraint on the detector design. Vector Boson pattern.
Another 5 minutes, Michel? I
think I will manage because I'm close to the end. The WW cross section at large MWW, which is going to be sensitive to give you access to the WW coupling indirectly. This is the study we did. And this is also a very interesting study, which is being pursued at the LHC to measure the VV-HH coupling directly. And the idea here is that you go to large di-Higgs invariant mass in the VBF mode. And the idea is that by doing so, you're suppressing the trilinear coupling behavior, and you're sensitive to these two diagrams, which in the standard model conspire to give you around 0 at high mass. So which means that any deviation you see from this is going to be in the tail of this MHH distribution, is going to be highly sensitive to a different C2V or CV coupling. And in principle, you could actually measure the C2V at FCC-hh with around 1% level precision, which is pretty impressive. This is again to strengthen the complementarity between FCC-ee and FCC-hh. You know that we need a strong first order rate-weak phase transition to explain the baryon asymmetry of the universe. In terms of model building, the simplest thing you can do is to build a standard model plus a singlet. And this shows you the reach for such models, direct reach, where you have heavy Higgs decaying to Higgses, and at the FCC-hh, and this tells you that, you know, with the full integrated luminosity at 100 TeV, you basically cover the full parameter space for such models, which are in this gray area. And here you can see the very same models, what kind of deviation they would give you in terms of Higgs self-coupling and Higgs to ZZ coupling. You can see that with the FCC-ee, you can actually measure this to 2 per mil, which basically kills most of the parameter space, and with the FCC-hh, you actually pin down on the other direction. So this would leave this very small corner of phase space for these models to live. But the nice thing is that you can actually probe them directly as well. So as a conclusion and outlook, so I hope I convinced you that the integrated FCC program allows for ultimate precision in the Higgs sector. So among all proposed facility, if you look at the combined program, it is the natural next step for a Higgs factory and for Higgs exploration in general, and will also, you know, of course, have large impacts in terms of exploration of BSM physics for the FCC-hh machine. Again, in terms of Higgs physics, the FCC-ee will produce around 1 or 2 million Higgs in extremely clean environment with low systematics, which will allow for model-independent extraction of the Higgs couplings of the most abundant decay modes. And the FCC-hh will instead produce 3 orders of magnitude, or even more, 4 orders of magnitude more Higgses, and 30 million Higgs pairs, of course, in a less clean environment with much larger levels of background. But this gives a very nice synergy because it allows to access the very rare decays that you are not able to access at the FCC-ee, TTH, which also you are not able to access at the FCC-ee. It gives you 5% precision on the Higgs self-coupling, and also gives you access to the Higgs in a new dynamic regime.
Okay. Thanks a lot, Michelle, for a very nice talk. And I think we have time for a couple of questions. So let me see if there are any hands raised. And I see Kajuri has raised her hand. So Kajuri.
Okay, thank you, Michelle. A very nice talk and interesting talk. I have been not keeping track so much. Just tell me, are you anticipating on an average 1,000 pileup events?
Yes, in the high Lumi phase, so the FCC-hh will have 2 phases, of course. There will be a low luminosity phase, which would be the equivalent of a run 2 at the high Lumi at the LHC, which will have a pileup equivalent to the high Lumi LHC, around 200 pileup, and then the high Lumi phase will have around 1,000 pileup. Yes. Yeah. This will be though for 2080. So by then we will probably have picosecond level time precision. Hopefully. So
studies which have been made, they assume that we will be able to get rid of these pileups suitably.
Yes, so, and in fact, we were careful in this sense because what you can see, especially in the single Higgs measurements, is that we are looking at extremely clean final state, so it's gamma gamma, mu mu, and for lepton final state, in the boosted regime where, you do not expect at all pileup to play a role there. For the Day Higgs, of course, is a whole different story. And Day Higgs, I think, is the challenge there, and will set the goal of detector requirements. And in fact, all these studies made with different levels of assumptions, which I show here, are, okay, what would happen if you were to, so typically the scenario 2 and 3 is if you were to have a similar performance to what you have today, or at least the expected performance you have today for Illumi, which I believe is going to be much better because historically this is what happens, right? So, yeah. But nevertheless, this says, okay, if you were to be really swamped by pileup, this is you lose at least a factor 2 in precision, right? Because there are several inputs which go into this. Your BB resolution will degrade, your diphoto resolution will also degrade, your B-tagging efficiencies will be worse, etc. Your photon to jet to photon fake rate will increase, etc.
So what is the USP for FCC-ee?
Sorry, what is the?
What is the main motivation?
For FCC-ee?
Yes, we are first going to have FCC-ee, and then
Why do we need FCC-ee? We need FCC-ee in terms of purely Higgs physics. I mean,
Yeah.
in
which are
FCC-hh.
the-
Sorry?
no, which are the main physics we shall be doing? So this is vector Boson scattering.
Let me answer in terms of Higgs physics. In terms of Higgs physics, if you do not have FCC-ee, you're not going to be able to measure the Higgs to ZZ coupling to very high precision, which means that all of your Higgs measurement at the PP collider are not going to be model independent. Now, if you ask me what is the advantage of FCC-ee as opposed to other linear collider machines, is another thing, which I might try to answer.
So in terms of model dependence, can you be more explicit?
Can I?
Be more explicit.
Well, in terms of model independence, is the problem is that if you don't have a recoil mass measurement, which is the one also Jenny talked about earlier, you are only going to be measuring branching ratios, even in the best case where you know the production cross-section to a per mil level precision, and the branching ratio always has the width in there, which needs you to assume something on what you do not see about the Higgs, right?
Okay, we have one more hand raised. So I think a quick question from Ram.
So my question is like for FCC-hh, like what will be the ultimate reach of this machine in terms of like say MSSM Higgs bosons? Like what maximum mass range is FCC-hh capable of achieving?
Well, okay, I cannot tell you the number right in my head. I can point you to the numbers later. Well, in terms of the pure direct reach, of course, you know, in terms of S-channel strongly coupled resonances, you expect like 40 TeV, right? Of course, MSSM is electroweak, especially like the, you know, if you are thinking about electroweakinos or winos or binos or this kind of stuff. So, for example, there is a preferred scenario for, you know, this disappearing track scenario where you have these very compressed spectra of, you know, you could actually discover a Higgsino of 1 TeV and Wino of 3 TeV, if I remember correctly, for example. But I can point you to some more precise statement if you want. But one very simple thing you can do is look at this slide here, and you can actually compare the reach by making the ratio here of cross sections and assuming your S over B is going to be similar. Okay.
Okay, so thanks a lot for Michelle again for giving a very nice talk. And with this, I think we will move to the last talk of the session.